Hi. So in this lecture, we have to start with chapter 3, that is work and heat transfer. But before that, let me mention few things which we left in previous lectures. The first thing is that when we studied the reversible process and irreversible process, there are few methods which make the process irreversible. So let's look at the methods which takes the process which makes the process makes the process irreversible. Okay, so basically there are two things. First is friction. If friction is present in the system, okay, if the friction is present in system, then then our process will be irreversible. And the second is there is free expansion. In case of free expansion, our system is irreversible, and we will see it in explanation in the upcoming lecture. Okay, and there is one more thing. When we studied the Kelvin scale, so we discussed that Kelvin scale is a absolute scale, and it takes only one point of reference, that is triple point of water. The thing is, now how does it work? How does if we keep one point as a reference, how would we calculate the further temperatures, next temperatures at required temperature, required pressure? Okay, so let's say for a constant volume gas thermometer, let's consider a thermometer. So we consider constant volume gas thermometer. So we know that in case of ideal gas, PV is equal to MRT. Since V is constant, P is directly proportional to T. We can get here. Okay, so we can say that P at triple point upon P at the pressure we require is equal to temperature at triple point upon temperature that we require. Okay, so let's settle down these three things. So we can calculate our required temperature using the temperature will be 273.16, that is triple point temperature of water, into pressure at which we require temperature, or pressure and triple point. Okay, so using this equation, so using this relation, we can calculate the temperature at any pressure. Okay, so next we will move to chapter 3. Chapter 3, which is work and heat transfer. In a closed system, the system can interact with the surrounding in two ways. Okay, the first way is work transfer. The second is heat transfer, and we will study these both topics in this chapter. Okay, so first let's start with the work transfer. So we will start with work transfer. We know a basic definition of work, that we studied in class 12th physics. That is, work is done by a force as it acts upon a body moving in direction of the force. Okay, so the work we obtain is the force we applied into displacement in the direction of force. Okay, but in thermodynamics we define it in a different way. So we define it as work is said to be done. Work is said to be done by a system if if the sole effect the sole effect on things external to the system if the sole effect on the things external to the system can be reduced to raising raising of a weight. Okay, so it means that work is only said to be done by a system if its net effect outside the system can be we can reduce the total effect on of the system on the surrounding uh, to to the raising of a weight. Let me show you the example. Let's say this is a system. Let me draw a system here, and we will reduce it in the required system. Okay, so 1 minute. So let's say this is a battery. So this is a battery, and from these two terminals we will connect a motor here. Let's say this is motor. Okay, so we will connect motor from these two terminals. Okay, so this is, let's say, cathode, this is anode or cathode. Okay, okay, so, and this motor is driving a fan. Okay, so let's say this is a fan. So consider this to be our system. Okay, this is a system. Now there is definitely a work taking place by the system on the surrounding. So there is a work, and what is that work? That it is driving the fan. Okay, but according to definition of thermodynamics, work is only said to be done if the sole effect on the thing external to the system can be reduced to the raising of a weight. So how can we reduce this to raising of a weight? Let's see here. I will copy this. I will copy this and again paste it here, and let me make some adjustment here. Okay, so what I'm going to do here is I am going to add a pulley system. So let's say that here I will add a pulley. Okay, okay, so let's say this is a pulley, and a weight is hanging from the pulley. Let's say W is the weight of this block. So when the motor will rotate, the pulley will be raised, or the weight will be raised. So it is directly reduced to raising of a weight. Okay, so here we can say that if this is system boundary. Okay, let me write the system inside the blocks in case of any misconception. Okay, this yellow thing is boundary, and outside the system, everything outside the system is surrounding. Okay, so here we can indicate that work is done by the system on the surrounding, that is our weight is raised. Okay, next we will see about look into the on the sign convention. What is the sign convention for work? Okay, so let's take a system. So let's say that this is a system. Okay, so if work is done by the system on the surrounding, we take it is positive. If his work is done on the system by the surrounding, that is we have to provide the work to system, so in that case it will be considered negative. Okay, now similarly we will study in the next about the heat interaction. So in the for heat, if the heat is provided to the system, okay, heat is added to the system, then it is considered positive. Okay, but if heat is released from the system, this is considered negative heat. Okay, so this is the work interaction and heat interaction between system and surrounding. You have to remember these sign conventions. Okay, and the simple and important thing, what are the units? So SI unit of work or heat, whichever you want, heat is equal to joule. Okay, and it is also written as Newton meter. Okay, generally work can be represented in terms of Newton meter or joule, and heat is generally represented in terms of joule only. Okay, so next thing we will do is fixed mass energy analysis. Fixed mass energy analysis, or it is also called closed system energy analysis. If there is fixed mass, then the system is closed. So in closed system energy analysis, we will first topic we will be seeing is, first thing is, what is non-flow work, or it can be also termed as boundary work, or it can be termed as closed system work. Closed system work. Closed system work. Okay, so let's take a example. Okay, let me just it. Okay, let me draw a PV diagram for you guys. So PV diagram. Okay, and let me draw a cylinder piston element here. Okay, so let's say that this is the initial position. Okay, and this is the final position. let me draw it again. Okay, like this. Okay, so this is point 2, let's say point 1, point 2, location 1, location 2. Okay, so let's consider a point in between. Okay, let's okay, so let's consider two piston at this location, and it moves from here to here. Okay, okay, so it moves a distance of dx. Okay, dx, or we can call it delta x. Okay, and corresponding change in volume will be delta v. Okay, let's say location A, location B, here it is location A, and here it is location B. Okay, so let's say that pressure at this point is P. So now we will move so mathematically we define work, that is delta W for a small displacement, as force into displacement. Okay, now we can write force in terms of pressure. Okay, so how do we write it in terms of pressure? Pressure into area of piston. Okay, into delta x. We can see from here that pressure into area into delta x can be termed as change in volume, small change in volume, that is delta v. Okay, so we can write delta w is equal to p times of dv, that is small volume change. Okay, so we can integrate it to obtain the net work, that is w is equal to integration of p dv. Okay, and we can write it as work done is equal to integration of p dv. So work done for a closed system is equal to integration of p dv from 1 to 2. Okay, now so let's see from this figure that we have drawn here, PV diagram. So we can say that P delta V, that is this is the area under the curve P dV. Okay, this thing is P dV. Now if we require total work, that is W, so we can say that it is the integration of all such area, that is it is the area of the curve, area under the curve that we have drawn. Okay, so let me write a definition here, line here. Let me adjust it a bit. Okay, so let me write it here. So area under the curve when projected on volume axis represents work for a closed cycle or a closed system. Okay, so area under the curve when projected on the volume axis represent work for a closed system. Okay, so we can see from here, even if in here, even if we keep the initial and final position same, but for different processes we will obtain different path. Okay, like these are different paths. So if so while going a different path, the area under the curve will be different, hence we will obtain different work done values. So work done is a path function. Okay, as we have discussed in earlier lectures. So next we will look into PDV work. The next topic is PDV. This is also a part of energy interaction or work interaction. Uh, I mean fixed mass energy analysis, which we have mentioned earlier. So let's talk first about topic was non-flow. What is non-flow work, boundary work, or closed system work? The second thing is non-flow work for various work in various processes. Okay, and since the non-flow work is depended by PDV, so we also write it is PDV work in various quasi-static So in these studies we generally uh, assume the process to be reversible and quasi-static process. Okay, so PDV work in various quasi-static process. So let's consider the first process. Let's say first process is constant volume. Okay, constant volume. Okay, so for constant volume process, we also call constant volume as isochoric or isometric. Okay, and from since in constant volume process V is equal to constant, so work done is represented by integration of PDV. So we can say that since V is constant, it implies that dV is equal to, in differentiation of constant value is what, 0. So work done will be 0. Work done is equal to 0. Okay, so in case of constant volume process, the work done is equal to 0. Now next is point B. The next process, let's say constant pressure. Constant pressure. In constant pressure, we also call constant pressure process to be isobaric or isopastic. Isobaric or isopastic. Okay, so in isobaric or isopastic process, since the pressure is equal to constant. Okay, so we obtain work using work is equal to PDV and integration PDV, and since the pressure term is constant, so we can directly take it outside the integral term. So P delta V integration of dV, yeah, here we will get integration of dV, and from point 1 to 2 we know that volume is a point function, so we can directly write work is equal to pressure times of volume V2 minus V1. Okay, so here it is. Okay, so third process, we will move to third process, that is C process. Isothermal process. So isothermal process is also called as constant temperature. Temperature process, or it can also be called as hyperbolic process. Okay, so in constant uh, temperature process, temperature is equal to constant. So we can write since PV is equal to MRT, so PV is equal to PV is equal to constant, and this, my friend, is the equation of isothermal process. Okay, or we can also write it temperature is equal to constant. This is also called the equation of isothermal process. Okay, so in case we want to, so since we require the value of work, so work done can be written as, and one more thing before that, on the we will show the constant isothermal process on PV chart. Okay, so let's draw a PV chart here. If we draw a PV chart for isothermal process, so we can see since PV is equal to constant is the type of a rectangular hyperbola, so we will will get curve like this. Okay, so this curve is, if we see, temperature is equal to constant or PV is equal to constant. Okay, so this is this process represent isothermal process. Next we will obtain the value of work for isothermal process. So work is represented by work done is equal to integration PdV. Okay, now from this equation we can write P is equal to constant. If we write constant to C, so C by V. Okay, so we will write it here, that is integration of C by V dV, and we can further reduce it as dV by V. Okay, so we will get C from point 1 to 2, if you calculate it, ln of V2 upon V1. So we will get work done for in the case of isothermal to be C times ln of V2 by V1, or we can also write it as C times ln of P1 by P2. Okay, now we will see what is the value of this C. Okay, since we have already written C is equal to PV is equal to MRT, we have already obtained it, and we can further write it as is equal to P1 V1 is equal to P2 V2. Okay, so this is the value of work for isothermal process. Okay, this also represent here, what is this term represent? This term will represent the area under the curve, PV curve. Okay, this area is represented by using this equation, and this is called the work. Next we will move to fourth type of process, D, that is adiabatic process. Adiabatic process. Okay, so in case of adiabatic process, you have to remember one point, that is heat transfer between system and surrounding is zero. All the walls of the system are insulated. Okay, there is no heat transfer between them, and the most basic equation for adiabatic is P V to the power gamma is equal to constant. Okay, now there are three conditions to apply this equation. Okay, let me mention them all here. So the first condition is process must be adiabatic. Okay, the second condition is process must be reversible. Okay, and the third condition is, is the fluid must be ideal gas. Okay, okay, for if these three conditions exist, then this relation is applicable for in the case of adiabatic. Okay, now what we will do, we will calculate the value of work for adiabatic process. So for work we will write, since it is closed system, so we will write work done is equal to pdv. Okay, but from here we can write pv की power gamma is equal to constant c. Okay, and we will obtain p is equal to c upon v to the power gamma. Okay, so we can write it as c upon v to the gamma dv. Okay, and we can further simplify it as c times of v की power minus gamma dv. Okay, so we can write work is equal to c times of, so we will when we will integrate this term, we will get v to the power 1 minus gamma upon 1 minus gamma from process 1.1 to 0.2. Okay, so we can further simplify it as work done is equal to c times of minus c by gamma minus 1 into so we can write it as v to 1 minus gamma minus v1 1 minus gamma. Okay, we can write it as this, and from this we can calculate so c times of gamma, we can substitute here c times of gamma is equal to, sorry, c times of okay, sorry, so we can put c is equal to pv की power gamma, and when we will multiply it by taking like p v की power gamma, and I have also written it as so let's say here I can write p is equal to c v की power minus gamma. So wherever there will be c p v की power minus gamma, we can write it as p in terms of p. Okay, so I will write here minus 1 upon gamma minus 1 times of p2 v2 minus p1 v1. Okay, so we can explain it in terms of p1 v1 minus p2 v2 divided by gamma minus 1. Okay, so this will be the expression for work done. Okay, now we can there is one more very important relation for adiabatic processes. I will just mention it here. Okay, so since we can use this relation and along with ideal gas equation, that is pv is equal to mrt, to write a relation which will be very useful in total of thermodynamics, and furthermore in in your power plant and IC engine along with RAC. Okay, so we will obtain T2 by T1 is equal to P2 by P1 की power gamma minus 1 by gamma is equal to V1 by V2 की power gamma minus 1. So this relation you must remember. Okay, this is a very important point here, and I will mark it as star. So you can directly use use this equation and this equation here, and you can like, let's see, obtain a relation between t and p, and also between, you have already have equation between p and v. You can obtain two equation. One is between t and p, another is between t and v. Okay, so when you will obtain both of these equations, you can directly write in this term. Okay. Now there is one more process. Let's say this is a fifth process. Let's say process E, which is polytropic process. This polytropic process is similar to adiabatic process. Only difference is that here there is a presence of heat transfer. That is, Q is not equal to 0. Okay. So this polytropic equation is represented by P v की power n is equal to constant. Okay, so instead of gamma there is a polytropic index n, which is considered in this equation. Okay, so let's move forward. We will, and one more thing, this value of n is theoretically it's between infinity to minus infinity. Okay, and when we calculate work for this polytropic process, so will be, since it is closed term, it is will be pdv is equal to, we can write p as c upon v की power n dv. Okay, so similarly we go to, in the case of adiabatic process, we will obtain our work done similar, only there is a slight difference. Copy, and I will just paste it here. What is slight difference? In case in the place of gamma, here it will be n. Okay, so there will be n minus 1. Okay, so this is a slight difference between the work done of adiabatic process and polytropic process. Got it? Okay, now there is one more thing. Since how we will make the graph for polytropic process, you can see that it will be also a type of parabola, but there will be difference similar to isothermal process, but there will difference between the difference of their slope. Okay, so we will look at the slope of both isothermal and adiabatic curves, like whether we're talking about adiabatic or polytropic, both will have a different slope. Okay, so let's talk about PV slopes. PV slopes. Okay, so first one is isothermal. We will talk about isothermal, and second is adiabatic. Okay, so for isothermal we know PV is equal to constant, and for adiabatic PV की power gamma is equal to constant. Okay, now we will differentiate both equations. So here we will get PdV plus VdP is equal to 0, and here we will get let's say dp v की power gamma plus p into gamma times of v की power gamma minus 1 is equal to 0. Okay, sorry, one more thing I forgot to mention here, right here, that is dv is equal to 0. Okay, so from here we can write dp upon dv is equal to minus p by v. Okay, and for in case of adiabatic we can write dp by dv is equal to minus gamma times p by v. Okay, So it means if we compare these both equations, let's say this is equation, this is dp by dv for isothermal process, this is dp by dv for adiabatic process. Okay, adiabatic. Okay, and if we compare these both equations, what we will get? We will get dp by dv for a adiabatic process is equal to gamma times that of dp by dv of a isothermal process. Okay, so you must remember this. So it means the slope of adiabatic curve on a PV diagram is gamma times that of slope of isothermal curve on PV diagram. So let me show a few processes here. So let me draw a rough diagram here. I will show you how the slopes are there. PV. Okay, so let's say there are two curves. One is this one curve. Okay, and the second curve is this. Okay, so since its slope is less, so t is equal to constant, and the next one is for adiabatic. So slope of adiabatic is more slanted than isothermal curve. Okay, so next I will what I will show you here, that show you the all the processes on a single graph for expansion and compression both on PV diagram. Okay, so let's make a big graph here. So we will make a graph. So this is pressure axis, this is volume axis. Okay, so we will divide it in 4 quadrants. Okay, and then we will draw all the diagrams. Let's wait for a bit. Okay, so let me take a pencil from here and let pencil color be done. So let's say this is the reference line here, and there is one more reference line here. Okay, so I will represent all the processes only here. Okay, so let's take the green color. So I will show you all the process for expansion. Okay, so there is one process constant, or let me take a red color. Okay, so this is your constant pressure. Okay, or let me take a thick line so that it can be visible. So this is the constant pressure process. Okay, and the next one is, what can we say? Next is, let's say, isothermal. Okay, after that we got polytropic, then our adiabatic, then our okay. So let me draw it first. I will explain to you later. Okay, so these are the curves that I have drawn. Okay, so let's leave that. Okay, so you can see that all these equations for either it is for let's say constant pressure, constant volume, isothermal, polytropic, adiabatic, can be written in form of PV की power k is equal to constant. Let me give something here. Okay, so all these equations can be written in form of PV की power k is equal to constant. Okay, so if we put the value of k here, and we will see what process it will become, okay, for different values of K. Okay, so let's put the value of K first to be 0. So if we put it is 0, then the process will become P is equal to constant pressure, okay, constant, okay. If we put the value of K is equal to 1, okay, the process will become isothermal, PV is equal to constant, isothermal process. Next, if we put the value of K is equal to N, that will be between 1 and gamma, so the process will become polytropic. If we put the value of K is equal to gamma, then the process will become adiabatic. Okay, now let's say the next thing, if we put the value of K is equal to infinity, then the equation will become V is equal to constant, that is constant volume equation process, okay. So for all these value of K, I will represent what that particular value represent, okay. So let's say this is K is equal to 0, that is constant pressure, K is equal to 1, that is isothermal, K is equal to N, that is polytropic, K is equal to gamma, that is adiabatic, and K is equal to infinity, that is isothermal, sorry, I mean isochoric or constant volume process. You can see it from here, right? And next, what I will draw is the all the process for compression, okay. So give me a minute, let me select a different color for this. So let's do it with this color, no, okay. So this is a constant, okay. So let's write it here. For the compression process, K is equal to 0. Here this will be isothermal compression, and here K is equal to 1. For polytropic compression, K is equal to 1. For adiabatic compression, K is equal to gamma, and finally for constant volume compression, K is equal to infinity. So I have represented all the processes, including for expansion and for compression, on PV diagram. You can see from here that value of K increases clockwise, ठीक है, K value increases from clockwise, whether it in case of compression or expansion, K increases in clockwise direction. So you can remember it in this way, okay. These are some types of work which are available, okay. So first one is electrical work, which can be calculated using voltage into current, okay. Next one is shaft work. Can be calculated by the torque into speed of torque, either by integrating it or directly. If the constant angular speed is constant and torque is constant, you can directly use T omega. Next is stirring work. Stirring work is when you stir, like if there is a system, like this is system, and you are stirring continuously, then you can either obtain work by mgh, that is the height to which the weight falls, or T theta with respect to motor, okay. Next is flow work. Flow work is for the open system, like we have already seen non-flow work, which is for closed system. Next is wire stretching. In wire stretching, you are always applying a tensile force F, so you can calculate the work by F into delta L, that is change in length. While integrating it, you will always get always, like this stretching work will always be negative, that is it will always be supplied to the system, okay. Next is surface film work. Surface film work can be obtained using sigma into dA, integrating sigma dA. And the final is magnetization of paramagnetic solid, and that is magnetized work. So we can define it as H into di. H is the field strength, and I is the component of magnetization field in the direction of the field. Okay. So if these works, if in question these works are mentioned and the value is not given, or value of like see here, like if your surface tension and change in area is provided, then you can directly obtain the value of work. Okay, we will move to the next topic. So next topic is free expansion. What is free expansion? When air is expanded against vacuum. So let's say that this is the system, and this is the system, and we have kept a partition. Okay, so this is the partition, and the system is completely insulated. One more thing, the system is insulated, and one side of partition is a gas, any gas, and another side it is vacuum. Okay. Okay, one side is vacuum. If you could suddenly remove the partition, if you suddenly remove the partition, what will happen? This gas, this gas will expand against the vacuum, and since there is vacuum, there is no resistance to the expansion. So the net work done during free expansion is equal to 0. Okay, net work done during the free expansion is 0. And one more thing, this is a irreversible process. This is a irreversible process, and all the irreversible processes are denoted by dashed line. Okay, in PV diagram I can represent state 1 and state 2 with a dashed line. Then this is a irreversible process. Okay. Now what we do generally, we started calculating the work using PDV, which we have used previously. Okay, so but in the case of free expansion, what is happening is that it is not a quasi-static process. The PDV work is for quasi-static. Okay, but the free expansion is a non-quasi-static process. Okay, although the initial and final states will be in equilibrium. Let's say I can say that state 1 and state 2 are in equilibrium. Okay, but what about the states in the middle of 1 and 2? They are not in equilibrium. Okay, so this is not a quasi-static process. Therefore PDV work is not, it cannot be used here. Okay, one more thing, that if you want to create such a system like it is also expansion against the vacuum, but there you should be able to use PDV work. So I can like you can do that. You can install infinite number of partition. This is only a theoretical concept, but you can install infinite number of partition, and you can start removing partition one by one from here. Okay, so the at end of every expansion, the system will obtain the point of equilibrium, and so the system, the PV diagram will come out to be continuous, and here you can obtain the work by using PDV equation. Okay, but for in the case of instant expansion or free expansion, the net work done is 0. Now we have discussed work, and we will start discussing the heat transfer. What is heat transfer? So we can write it as heat is also a form of energy. Okay, so heat is a method of energy interaction which takes place due to the virtue of temperature difference. Okay, so heat transfer takes place due to virtue of temperature difference. Okay, so this is the definition of heat transfer. And So in case of heat transfer, the specific heat uh, is a term that we will come across frequently. So what is specific heat? We can write a definition for specific heat. This specific heat is defined as the heat which is required, heat, or we can say amount of energy, F, energy required to change temperature temperature of unit mass of substance, unit mass of substance by unit Kelvin. So amount of heat which is be required to temperature the to raise the temperature of unit mass of substance by a unit Kelvin is will be called specific heat. Okay, and the specific in if we talk about the gases, then the specific heat at constant pressure is greater than, always greater than specific heat as constant volume. So how can we see let's take this two example, one at constant pressure and one at constant volume. Okay, so let's talk about both the things. So let's take this as the at a constant pressure. Okay, so if P is constant, what will happen if we let's say we are supplying some heat. So if we apply the heat, the uh, temperature of the system will increase, and with that the piston will also move upward to maintain constant pressure. Okay, so it means that for the heat transfer at constant pressure, we will require to amount to required require two things. First one is this Cp will I mean this Cp which we use to represent the specific heat at constant pressure will include two things. One is that it will include the boundary work. Okay, work done due to the movement of piston. And second thing is it will also include the internal energy change. Okay, due to temperature change. And if we take the closed system, then here volume is equal to constant. So only one thing is happening, that the temperature is increasing. Okay, while we provide heat to increase the temperature, pressure is also increasing. But the main point is that with the help of heat that we are used to supply the system, with with the heat's help, only temperature is increasing. Here with this here heat's help, temperature is increasing, also a work is done. Okay, by the system on the surrounding. So Cp is always greater than Cv. Okay, so we can so it is also written in terms of like uh, mathematically it is given that Cp minus Cv is equal to R. Okay, you can also see from here that Cp is always written as Cv. So but this is for further lectures, it won't be included in this chapter, so I won't be discussing this anymore. And we can write specific heat expression as Q upon m into delta T, that is having unit of joule kg Kelvin, joule per kg Kelvin. Okay, so we can calculate heat transfer using Q by mc delta T. Okay, next now let's discuss one more thing, and that is energy interaction equation. So total energy interaction of the system can be written in two forms, that is macroscopic plus microscopic. This macroscopic term include bulk uh, bulk energy, that is let's say example, for example, kinetic energy and potential energy. So this can also be written as bulk motion energy, and potential energy can be termed as bulk position. Okay, so this kind of energy is called microscopic energy. Okay, and microscopic energy is also termed as internal energy. Now there's various forms. First one is, let's talk about sensible energy. Second is latent. Okay, and the third one is, let's say, chemical. Fourth one, let's talk about nuclear. Okay, so this type of energy and there are many more, and this type of energy is called microscopic energy. Okay, so sensible energy is due to the change in temperature. Okay, latent energy is due to it is a hidden energy, basically hidden in the substance, and it is occurs when there is a phase change. Now we will discuss one more thing, and then complete this lecture, and with that we will be ending our lecture for chapter 3, that is work and heat transfer. So there's one more before that, the phase change can be both equations. Sensible heat can be written as Q is equal to mc delta T, and the sensible latent heat can be written as m into L, mass into latent heat. Okay, now this latent heat can be of sublimation, vaporization, or fusion, anything. So let's consider one more thing before ending this lecture, that is let's see about the melting of the ice and including superheating. Okay, so let's assume that there is a ice block at 10 degrees Celsius. Okay, now if we are considering the melting of ice, then there are various things which we should consider. If ice is at minus degrees centigrade, then it will first move to, while heating, it will first reach to 0 degree centigrade ice. Okay, if I talking about 10 degree Celsius ice, then after that it will reach 0 degree Celsius, again ice. After that it will absorb some more heat, and then it will reach 0 degree Celsius water. Okay, then after some more heating it will reach 100 degrees Celsius water. Okay, then after some more heating it will reach 100 degrees Celsius, and this will be in water vapor. Okay, and then if we heat it further, then let's say 150 degrees Celsius, then it will be superheated steam. If we have to calculate total amount of heat that is expended in this total process, so we can do it by like this. So here you can see that only temperature changing, the phase remains same, ice to ice. So we can write here Q is equal to m into specific heat, mass of ice block, into specific heat of ice, into change in temperature of the ice, that is 10 degrees Celsius. Okay, now here the temperature remains same, but the phase changes. So here what we got, there was sensible heat, here it is latent heat. You can write it as Q is equal to m into latent heat of water, of ice to water. Okay, now next, water to water, 0 degrees Celsius, 100 degrees. So this is sensible heating. You can write Q is equal to mc of water into delta T. Okay, now here also again, water to water vapor, that is latent heat. So Q is equal to m into latent heat of water to water vapor. Okay, now here again it is water vapor to water vapor, only superheating. Okay, so this is sensible heating, again latent heating, sensible heating, latent heating, sensible heating. Okay, and here again it is Q is equal to mc of steam into delta T. Okay, so if you receive some questions which will include the melting of ice or heating of ice, then you should use do it like this. Okay, so with this we will be ending this lecture, and in next lecture we will discuss some questions from this chapter. Okay, thank